Welcome viewers. In this video we are going to do design of transmission line tower foundation type 1 pad and chimney using Indian standard. This is part 4 out of 5. In this we are going to do design of chimney. Before going to watch this video, we request you to watch your previous video. In the part 1 we have discussed about the tower geometry, design foundation loads, soil parameters, foundation geometry, and finally we did this uplift resistance check in part 1. Followed by that part 2 we have completed the bearing capacity check. In the part 3 we covered sliding and overturning check. This is part 4. In this we are going to see design of chimney, and finally followed by the next part, that is part 5, we are going to do design of base slab. With that the entire transmission line tower foundation for type 1 pad chimney using Indian standard get completed. So before going to watch our previous video up to part 3. The video link is given in the description. You can find in that. Also the design of stub angle using American standard also well explained in another video. That video link also provided in the description. You can go through that before coming to this part 4 so that you can able to understand the series of calculation methods which is required for this foundation for transmission line tower. So let we will move and look into that Excel calculation. Design of chimney involves majorly the 5 steps which is showing in the right hand side. First one is reinforcement assumptions. In that we need to assume the reinforcement, say for example number of bars and diameter of the bar we need to assume. So that assumptions which we have considered is similar like this pattern, having a 6 number of reinforcement in every side. The second step is the compression with bending in a normal condition, and the third one is compression with bending for broken wire condition. Followed by that tension with bending we need to check for normal and broken wire conditions. So these are the 5 steps we need to do for design of chimney. First one is number of bars. We had already considered the 20 number of bars in 20 mm diameter. Area of the steel in compression we can consider the 20 number into BID square by 4. Here we are considering the diameter in centimeter. So this 20 mm we are dividing by 10 to consider as a centimeter, 2 centimeter. So applying this BID square by 4 into number of bars formula, we are getting 63 centimeter square. Calculating the percentage of steel is AAC, that area of steel in compression divided by the concrete chimney size, which is a 700 mm in both the direction. So divided by that cross sectional area we are getting 1.29 as a percentage of steel reinforcement. Then we need to check that reinforcement which we had considered, the percentage of reinforcement 1.29 with the standard requirement. So for that we need to refer the class 26.5.3.1 of IS 456-2000, page number 49 to be referred. So here in the right hand side you can see a PDF file which is opened, 26.5.3.1 class longitudinal reinforcement for columns. It states that the cross sectional area of longitudinal reinforcement shall not be less than 0.8% nor more than 6%. So here you can see that the minimum percentage is 0.8 and maximum is 6. So the same case we are considering here as a minimum reinforcement is 0.8 to maximum is 6. Our case, as we had assumed that 20 numbers of 20 mm dia, which is 1.29% of the steel, a percentage of steel with respect to the cross sectional area of concrete chimney, which is in between this minimum and maximum range. So hence what we had assumed is correct in line with the class is 26.5.31 of IS 456-2000. So next we can do for next step compression with bending for normal conditions. This check we need to do to find the both the bending actions in both the directions. It is a biaxial bending by considering the axial force also. That is, in this case we are going to consider only the compression, and there is other separate two cases we are going to do with the tension with bending also. So now let me look into that how to do the calculation. For that, P divided by FCK, that is the percentage of steel divided by the grade of concrete or the concrete compressive characteristic strength, we need to divide it. So 1.29 is a percentage of steel divided by the concrete characteristic strength FCK, we are dividing here, which is a 25 megapascal. For that we are getting 0.06. So next we know that the compression, that is a down thrust of the foundation, which we had calculated from the structure load, is which is also factored as 1.2 is 56,533 in kgs. So that we are converting into Newton by multiplying 9.81. So this formula, actually this value we need as per the chart 44 of SP16. So for that, page number 149 should be referred. In the right hand side you can see the SP16. In that page 149, the chart 44 is stating compression with the bending rectangular section, reinforcement distributed equally on four sides. So as you see here in our picture, there are 6 number of bars in which are viewable in all the four sides. So it is equally distributed reinforcement kind of column. So this PU by FCK BD, which is in the left hand side of the Excel sheet, we need to find out. So for that, this PUC is nothing but it is a compression down thrust, which we have seen here. So it is 55, 45, 89. So this value divided by FCK 25, we know 25 megapascal, divided by 700 are the cross sectional area, that is B into D of the chimney. So we are getting 0.046 as a value for this. We can assume the clear cover of 50 mm. Then D dash is nothing but the diameter we are assumed is 20 mm. Half of the diameter plus the clear cover is the D dash, as it is defined in the SP16. So the D dash by D, that is 60 by 700, we just make it this as a ceiling as a 0.05. So D dash by D is 0.1. So this graph we need to see here. If it is D dash by D equal to 0.1, we need to consider this chart 44, or else if the D dash by D is equal to 0.05, then we need to consider chart 43. So depends upon the D dash by D, we need to find out this chart, which chart relevant chart is we need to consider. Also the steel grade also we need to check. It is a 415. So in our case also we had considered 415 as a steel grade. In the Excel sheet you can see. So our exact chart we need to refer is 44. So in that you can see PU by FCK BD, the value is 0.06, and the percentage of steel divided by FCK value is 0.06. Okay, that PUC by FCK BD is 0.046. So that will laid here in between here, and this value 0.06, which is coming from this curve. So it is exactly laid on 0.1. So here if you draw a straight line for 0.046 and 0.06, it will come in 0.1. So that mu divided by FCK BD square, the value can be, we can consider 0.1. So this is what considered here. And we need to find out the mu(x1), that is bending capacity of the column, by considering the reinforcement and all the parameters which we had calculated just above. So with that mu(x), if you are applying 0.1, which is we extracted from the graph or chart 44, is 0.1. So mu(x1) is nothing but 0.1 multiplied by FCK/BD square. So FCK is 25 and B is 700 mm, D is 700 mm. So that square we are multiplying. So this value will be in Newton millimeter. So we need to find out in kilonewton per meter, means we need to divide this by 1 million. That is 1 followed by 60. Because for Newton to kilonewton we need to apply 1000. We need to divide by 1000. By converting from millimeter to meter, we need to divide again with the 1000. So totally it is 1 followed by 60 to convert a Newton millimeter to kilonewton meter. So that is what done here. As this is a square chimney having a equal reinforcement, whatever the consideration which we are calculating this bending moment capacity in x direction is applicable for y direction also. So my1 also we are considering as the same 857.5 kilonewton meter. Next we need to calculate the actual bending moment which is happened in the bottom of the chimney. So for that, one moment which is caused is due to the side thrust. So there are two side thrust. So here you can see one is in a transverse side as per the design foundation loads. Second one is longitudinal side thrust. So both the side thrust will be act at the depth of 2.4 plus 0.3, because that transverse force which is going to apply in the top of the chimney, which is above 300 mm from the ground level, plus the below up to this slab, the 2.4 meter height we need to consider. So the effective moment causing for the chimney is at 2.7 meter. So we are multiplying that side thrust into the 2.7 meter. Also we know that there will be some soil effect which we had calculated in the bearing capacity calculation. So that the soil effect also we need to consider, because that soil effect will be resist the side thrust. So here the resisting soil force under normal condition for transverse side thrust we had calculated under the bearing capacity check. So that we need to consider. The height we need to consider for the same. So this height we need to consider. For longitudinal case, this is a height we have considered. So now, so by applying this 9166, which is a side thrust in a transverse side multiplied by the effective depth 2.7 meter, deducting the resultant soil pressure, that is the weight of the soil in a normal condition, transverse side multiplied by the, that is a 7401.4 kg multiplied by the 2.4 meter depth, which is a soil pressure acting depth. we are getting 18,827.08 kg meter, that we are multiplying or dividing, that we can multiply it by 9.81 divided by 1000 or directly divided by 101.97, we are getting 184.7 kilonewton meter. Similar, like for longitudinal thrust also we need to apply this kind of method, so that longitudinal side thrust multiplied by 2.7 meter, which is a clear depth of the chimney. Soil weight for broken wire condition, which we had calculated for bearing pressure check. Anyway, that soil weight is remain same for all the cases. So here also that 2.4 meter depth we need to consider for side thrust, longitudinal side thrust. So again MUY, which is for longitudinal side thrust moment, these are the moment, 169.47 kilonewton meter. Next, after calculating this moment due to lateral thrust and the soil resistant forces, we need to check this member subject to combined axial and bending, biaxial bending, using this equation, which is given in the class 39.6 of IS 456-2000. So for the page number 72, we are referring here in the right hand side PDF file. So you can see this equation we need to follow in order to check that combined axial load and biaxial bending. So here MUX divided by MUX1 whole power alpha n plus MUY divided by MUY1 whole power alpha n, which should be less than or equal to 1. So here the definition for MUX and MUY is given as it is a design load or moment in both the x and y axis respectively. MUX1 and MUY1 are the maximum uniaxial moment capacity of axial load of PU bending moment with respect to y and x-axis respectively, and the alpha n is equal to Pu divided by Puz, whereas Puz formula is given here as 0.45 FCK, which is a characteristic strength of concrete, into AC is a gross area of the concrete in chimney, plus 0.75 Fy is the steel yield strength 415 megapascal. ASC is the area of steel in compression. So this is an equation to find out Puz, and Pu divided by Pu is at this value, generally ranging from 0.2 to 0.8. For this value we need to consider alpha n as linearly 1 to 2. So this we are going to look how we are going to work on that. So you can see in the left hand side the Excel sheet Puz we are calculating based upon this equation 0.45 FCK. So we know that FCK is 25 megapascal and AC is 700 by 700, which is the size of the chimney, and 0.75, this 415 is the Fy, that yield strength of steel, and ASC is we are calculating by d square by 4 equation for circular diameter of the rod reinforcement which we got provided. Alternately, we can directly pick from that calculated area, which is a 63 centimeter square. So by calculating this, we are getting Puz as 7468141 Newton, that divided by 1000 we are getting 7468.15 kilonewton. So this is a resisting axial forces of concrete based upon its material and the cross-sectional area. Next one is we need to calculate the PUC. PUC nothing but it is a PU in terms of here in this right hand side PDF file. So this PUC we need to get from the data which we are already having from the structure loadings. So it is a down thrust that we are converting into a Newton, a kilonewton from kg, so that divided by 101.9. So that is we are getting 554.8 kilonewton. So we are dividing this PUC by PUZ as per this equation given in the right hand side PDF file of IS 456 2000. So the value is 0.075, so which is less than 0.2. So in this case we can consider 1, because here in the right hand side PDF it is stated that for values less than 0.2 alpha n is 1, for values greater than 0.8 alpha n is 2. So this formula is developed or formed in order to fulfill this right hand side conditions. So if it is this PUC by PUZ is exceeding 0.8, then this value will come as 2. If it is less than 0.2, then this will be 1, or it will do some interpolation method, linearly interpolation method for 0. If the value is in between 0.2 and 0.8. So we are getting the value alpha n as 1. So we are simply applying these values here in this equation as per the right hand side PDF it is showing here. So this MUX we are already calculated, which is a design load from the chimney or through structures. 184 and this 169.47 are the MUX and MUY respectively, and accordingly we had calculated this bending capacity based upon that chart 44 in SP16 code. So that we are applying here as a MUX1 and MUY1. Both the values are same, as the chimney is a square of equal side reinforcement, equal longitudinal reinforcement we got provided. So now equating all this, the factor is 0.41, which is less than 1, hence safe. So this kind of calculation again we need to apply for the broken wire condition. Here that PUC we need to consider from the structural loads, design loads, as a case for broken wire condition. Here you can see this 5459 is the broken wire condition down thrust. So that we are dividing with the, that we are going to find out that PUC divided by FCK BD. Again we need to refer chart 44 in SP16. So page number 149. So this chart we need to refer. So in this chart for 0.1 PUC FCK BD and for PU by FCK 0.06 we are getting the value as 0.08. So applying that we can able to find out the bending moment carrying capacity of the chimney. So here also that MUY1 and MUX1 both are same, as it is a square chimney and with equal reinforcement in all the 4 sides. So the same philosophy we are going to calculate here, but the thing is the broken wire condition lateral forces we need to consider in order to calculate the actual design moment. So we know that transverse side thrust is 2743 for broken wire condition, and that multiplied by the total depth as we had calculated for normal condition. The same procedure we need to follow, only the forces is going to change. Instead of normal condition it should be considered as broken wire condition. So this two depth 2.4 and 0.3 meter we need to consider as a lateral force acting height from the bottom of the chimney. So this alone we need to consider the weight of soil in broken wear condition for transverse side thrust, and the respective height is 1.5 meter. So we are considering this 1.5 meter here. So that MUX is 58.5. So similar like the same way we are going to calculate the lateral thrust in MU direction. So this is a longitudinal thrust for broken wear condition. So this force we are considering 2453. So that multiplied by the top to bottom of the chimney clear height 2.7 meter, and this is again the soil weight, and this 1.4 is for broken wear condition for lateral side thrust which we had calculated for bearing pressure check here. So it is a 1.4 meter, and this soil resisting force we need to consider as per the broken wear condition longitudinal side thrust. This soil force we need to consider. So accordingly the MUY is 53.43. So that PU is that we can consider the same as consider as per this, because the cross section and the reinforcement and concrete grade are remain same. So again we need to check this class and applying the calculated moment using this PUC, PUZ, alpha n value, and this moment which we had calculated MUX, MUY, MUX1, MUY1. So all those we need to apply here and finding the interaction factor is 0.16, which is less than or equal to 1, hence is safe. So with this, that the compression with the bending for two cases, that is normal and broken wear condition, is completed. Next we need to do tension with bending. So coming to the tension and bending, normal tension, first we need to find out the tension which is coming from the structure. So that we already know that it is there in the design foundation loads tab. So uplift is 64,841, that we are converting into Newton, which is here we are multiplying with 9.81. So according to the requirement of the SP 16, the chart 79, we need to find out these equations. PU divided by FCK BD. So we know that FCK is 25 megapascal and B and D are 700 mm respectively. So we are getting 0.05, and we know that P is 1.29. P is a percentage of reinforcement steel, which we had already calculated here in the compression with the bending before that. That is our first step which we had calculated, the reinforcement assumption. And P divided by FCK is nothing but the 1.29 divided by 25. 25 is a 25 megapascal is a characteristic strength of concrete, and D dash by D, which we had calculated earlier. So these are the requirement in order to find the value of MU by FCKBD square from the chart 79. So refer to the chart 79. This is chart 44 of SP16, which is showing in the right hand side PDF. So for that, page number 184 we need to refer. So here you can see the D dash by D is 0.1, and the PU by FCKBD, as it is 0.06, we need to refer this third curved line. So with respect to that 0.06, and the PU by FCKBD is 0.05 here in the Excel sheet. So for 0.05, which will lay here, if you draw a imaginary line between this, so here if it is 0.1, then 0.2, 0.4, then 0.5, 0.05 will come here, So touching this 0.06, if you are dropping down to the chart, the value is coming 0.6. So it is 1, 2, 3, 4, 5, 6. So 0.06 is a mu by FCKBD square value. So that we are entering here. Then as usual, we need to find out that MUX value. So it means we need to multiply this FCK, where this denominator will go to numerator. So likewise, this equation we need to apply the same which we did for compression with the bending cases. So finally we are getting MUX1 and MUY1, because that MUX and MUY we can consider the same moment carrying capacity which is calculated here, as it is a square and equally distributed reinforcement. Then this MUX and MUY we can consider from the calculation which is done for compression with bending, because the bending never going to change, because the bending is happen only due to the side thrust. So the same value we can consider for normal condition, mu and mx. Then with the reference to the IS 456 class 39.6, same which we had done for compression and bending, the same equation we are going to apply here. So then here in this factor is 0.69, because this MUX by FCK BD square value from the chart in case of tension with the compression get reduced. Here in the normal condition you can see it is 0.06 we had considered for tension with bending, but in the compression with the bending the value is 0.1, which is higher than that. That means that bending moment carrying capacity will be more in terms of if the concrete column is subject to both compression and bending, but if it is subject to tension with bending, then the bending moment carrying capacity will be reduced. So that is what the intention is, because that concrete is weak in tension and strong in compression. So that is a main philosophy which is coming here. That's why the interaction factor of bending moment, actual bending moment divided by the bending moment capacity of the concrete chimney is higher in tension with the bending cases, but in case of compression with the bending for normal condition it is 0.41. Here it is 0.41 and here it is 0.61. So similar like we need to do for broken wire condition also. So the broken wire condition we need to take this PUT, that is tension value as per the broken wire condition case. Here you can see that 11,817 is the broken wire condition uplift forces, that is tension forces, that we are converting into Newton by multiplying it by 9.81. And similar the same as a procedure for a normal condition we are applying here. PU by FCKBD we need to calculate as per the chart requirement. So 25 megapascal into 700 mm square as a BD value. So here it is 0.011, and that P and P by FCK and D dash by D remain same. So with respect to the chart SP16 chart 79, again we need to check for 0.01. So 0.01 lies here in the half of this, and we need to up down, and coming to that it is coming near to 0.65 or 0.7. So we can consider 0.7. So 0.7 into FCK is 25 megapascal, and BD square we are applying here divided by 1 followed by 10 0, that is 1 million. We are getting, in order to convert this Newton mm to kilonewton meter, it is a 600.25. So again this is as a square and equally reinforced column. We need to consider both the bending moment capacity remains same, and here as usual that MUX we need to take from the broken wire condition which we had calculated for compression with bending. So this value we need to consider same, and we are checking those with the class 39.6 of IS 456 page 72 for the interaction factor. So here page 72, which is already showing here. So the same equation we are going to apply for tension with bending. So here it is coming 0.19. Again you can check with the broken wear condition for combined compression and bending. So it is 0.16, but here it is 0.19. Again it is a little bit higher interaction factor. So this is all. With these 5 steps we had completed the design of a chimney. So with this part video get completed. Thank you. Look description for more related videos. Subscribe to this channel for more updates.